Sir, but whatever the screen you are sharing, actually it's not good, sir. Okay.
Oh, is it visible?
Now it's okay. Actually, it is alternating between like zoomed one and normal one.
Oh, okay.
I don't know if others also face the same problem.
Can others confirm? Is there a problem in screen
Sir,
share?
it is normal.
It is normal. Okay. Okay.
Okay, sir. Then I think for me only there is some problem, sir.
Okay. 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 Good morning and welcome to lecture number 40. Yeah. So yeah, now the news is Moodle is back up. There might be some data missing. I mean, some of the marks updates are not reflected. We are looking into it. But I suggest that all those who haven't yet submitted the solutions, please submit through email. Okay, so let's not submit through Moodle this time, because I'll just have a trial of how this happens with email. Okay, so I'll just, by tomorrow evening I'll know how to arrange and so on. Okay, so I haven't handled so many emails at one shot. So yeah, for assignment I will stick to Moodle, but I'm thinking of considering endsem through email. Okay, so let's see how this goes this time. Okay, so how difficult it is to arrange and so on, because I'm afraid that I might miss some emails. That's why I wanted you to write the subject line, the QP code. Okay, so that I can put a filtering. Okay, so yeah. So those who, I mean, forgot about their questions and all, I think must have been there. I think it was there since afternoon yesterday. I'm not very sure. I mean, Moodle was up a day ago, but the data was not there. Okay. In the last lecture, we were looking at a relationship between min-cut and max flows. So min-cuts are kind of dual objects to flows, or cuts are dual objects to flows. It's basically, a cut is nothing but a partition of the vertex set, and the cost or capacity of the cut is the weight or capacity, total capacity of the edges that cross. Okay, but only thing is we are interested in only one direction, that is S to T. Okay, sorry. This is an example of an S to T cut. Capacity of the cut is 15. So like we saw in the last lecture, cuts and flows have close connection. Okay, and being dual objects, the objective is to minimize the weight of the cut here. Okay, so, or minimize the capacity of the cut. Yeah, so please pardon me if I use the term capacity and weight interchangeably here. Okay, so whenever I say weight, I mean capacity in this context. So here the problem is given a directed graph and two distinct vertices, S and T. We assume that there are edge capacities. We'll always assume them to be non-negative. We want to compute an S to T cut of minimum capacity. Okay. So in the last lecture, we were looking at relationship between max flows and min cuts. So yeah, so for this example, it so happened that the min cut value and the max flow value are the same. Okay. So this is not just a coincidence. In fact, it is true. So in the last lecture, we saw that if you take any feasible flow and any S to T cut, okay, the value of the flow, remember the value of the flow is the net outflow of vertex S or net inflow of vertex T, that is destination. The value of the flow is bounded by the capacity of the cut. Okay. So this essentially followed from definitions of value of flow, and yeah, that's essentially it, a bit of manipulation of the sums, okay, and bounding them suitably. So only question that remains is, so what we have is, okay, take any feasible flow, its value is not going to be beyond the cut. Now one fundamental question is, Okay, can you guarantee that such a flow which matches this with equality exists? So from the proof that we saw in the last lecture, you might have figured out when the equality holds, right? So there were two places where we used inequalities. If both places it holds with equality, then we are pretty much sure that this will be equal to the capacity of the cut. Okay. But the question is it always achievable? For a given graph, okay, what is guaranteed by this lemma is it's at most the capacity of the cut or minimum capacity of a cut. In fact, at most capacity of any cut. So you take the minimum. So, and you can maximize here, or in other words, max flow is at most the capacity of the cut. The question at that point of time was, okay, is it achievable? Okay, so that was a surprising result that is due to Ford and Fulkerson. So like the shortest path algorithms, there were many others who invented the same thing too, though Ford and Fulkerson kind of did it independently. Ford is the same person as the shortest paths algorithm. Okay, so it's the same researcher. So they proved max flow min cut theorem. So if you take any flow network with the non-negative capacities and two distinct vertices S and T, the maximum value of an ST flow is equal to the minimum capacity of an ST cut. Okay, that is, the maximum flow indeed achieves this with equality for any flow network. Okay, so that is the interesting point, or the what we can say as surprising part, because from the proof that we have seen, it was not clear will equality be met. Okay, at least if you go through the proof line by line, it's not apparent why equality should be met. It seems like requiring an argument. Of course, it is indeed true. I mean, it requires a fairly non-trivial argument to prove this statement. Okay, so this gives us the complete dual relationship between the two. Okay, so this is a maximization problem and this is a minimization problem, and the values match. The min and max values, they match, they are equal to. Okay, so the moment you get a minimum weight cut, you know that that is going to be your flow value. You can't go beyond that. Okay, so now rest of our lecture today is about proving this theorem. Okay, so we'll prove with and also demonstrate it with the examples, and towards the end we'll also see applications of max flows. Okay, so yeah, so the interesting part is network flows have immense applications. I'm only going to give a couple of, I mean, in fact, only two of simplest applications. There are lots of non-trivial applications. Like I said in the previous lecture, there is a whole book dedicated to network flows. Okay, so there is a book on network flows. Sorry. I'll write it as additional reference because this is, yeah, I haven't referred to it right now. A book by Ahuja, Ravinder Ahuja, Magnanti, and I think O'Reilly. I'm not very sure about the spelling. Okay, network flows and algorithms. It's a huge book. It in fact covers most of the network flow algorithms and their applications in a very, very detailed fashion. There are also other books on the same topic. One book is titled Network Optimization. So like I said, I mean, network flows, they kind of arise in operations research and in fact also combinatorial optimization fairly often. And they happen to be like closely connected to shortest paths, matching, and so on. And hence they find wide applications. Okay. So for this course, ideally I would have liked to deal with a couple of algorithms on the topic. Okay. And in fact, network flows also satisfy nice structural properties. So yeah, since we don't have much time and this this semester is like a toned down semester. So we will only prove this theorem, and we'll see that this immediately gives us an algorithm. We will not see more efficient algorithms, or we won't see any efficient implementation of it. I'll just state the algorithm. I mean, I'll just tell you that, okay, this immediately gives us an algorithm, and that's it. Okay, so we'll not see anything further. And I'll briefly discuss one or two applications of it. Okay. Okay. So the fundamental thought process here is so the notion of reduced graph. Okay. So given a flow, you obtain a new graph with the new capacities. Okay. And then if you look at certain paths in that graph, that is going to tell us if the flow that we have already in hand, is it optimal or not. Okay. So before going to the details, I'll just start with one assumption. Okay. So we'll assume that, just to simplicity, I mean, in the end, I mean, in fact, we'll be dealing with such graphs too. But for the sake of argument, it's easier if you have this assumption. Okay. So we'll not have this kind of edges, parallel edges, back and forth. Okay. U and V. Okay. So in such situations, we'll assume that one of the capacities is zero. Either this is zero or this is zero. Now, in a general network, why do we assume that? Okay. So if there is a scenario where these are non-zero, you can always modify the network such a way that you can assume there is no forward and reverse edge between a pair of vertices. Okay. So let's just see how to do it. So this is capacity alpha, this is beta. Okay. So what you do is you just subdivide the edges. Okay. So these are original vertices U and V. So I introduced two new vertices A and B. So the capacity remain the same, alpha alpha, beta beta. Okay. This is my UV. These are the new vertices A and B. Okay. So this local modification does not really affect flow, in fact. Okay. So only thing is these new vertices should not be connected to anything else. Okay. So then it won't affect the flow at all. If there was a flow, say alpha prime along this, I can have alpha prime along this. Similarly, if there was a flow beta prime along this, I can have beta prime along this. Okay. So with this modification, without loss of generality, we can assume that for any pair UV, either cost of UV is 0 or cost of VU is 0. Okay. Even if there are, when I say cost is 0, that not cost, I'm very sorry, capacity. Okay. Capacity. When capacity of an edge is 0, that means that the edge is non-existent, because you can't do any, you can't assign any flow to that edge, right? So it's as good as saying that the edge is non-existent. Okay, so you have only one direction edge. So with this modification, we can always assume that the network does not have such edges. Okay, so back and forth with the non-zero capacities. Only one direction will have non-zero capacity. Okay. The idea of reduced graph is the following. Okay, so let's just go back and see, look at our flow assignment. Okay, okay, maybe I'll just stick to this picture. So here you have, so let's just focus on original flow that we had assigned, not the optimal one. Okay. See, how do you, first thing is, okay, how do you see that there is no better flow? Okay. Or how do you see that this is maximum? Well, if we prove the theorem, then we know that, okay, the weight of the min cut. Okay. But that's what we want to prove now, right? So we haven't yet proven that. Okay. So the idea is the following. So you obtain a graph, what we call as a residual graph, okay, which kind of helps us in understanding what are the possible reroutings of this flow, okay, so that if the current flow is not optimal, that is not maximum, there is always a possibility of rerouting so that you get a better flow, okay. And when there is no further rerouting possible, then we'll see that in the residual graph, if you look at a cut, so there the residual graph will correspond to a cut, okay, which separates S and T. And then it's just one line of argument saying that, okay, so the capacity of the cut will be equal to the value of the flow. Okay. So there is some counterintuitivity in the definition of residual graph. I hope it will be clear when we look at the proof and give examples. Okay, so I'm going to define the residual graphs now. So is there any question so far? Okay. So GB any flow network, say C is the capacity. Okay. So the assumption is, I mean, capacity, we always, I mean, I defined it as capacity from edges. So we assume that for any UV, any pair UV, capacity is defined. If the edge is non-existent, the capacity is 0. Okay. So let F be any feasible flow with the feasibility condition, that is conservation property plus within the capacity. Okay. For every edge, the flow should be less than or equal to the capacity. So the residual capacity of G with respect to F is defined as follows. Okay. So we denote this as C sub F. Okay. So to indicate that the residual capacity is dependent on F. Okay. So it is defined based on the following conditions. So if UV is an edge in the graph, okay, so then the residual capacity is basically what it means. Capacity minus the actual flow. Whatever you can assign further. Okay. So for example, in this example, here residual capacity will be 20 minus 10. Residual capacity will be 5 minus 0. Residual capacity here will be 0. 10 minus 10. This will be 10 minus 0. Okay. But there is also one counterintuitive element to it here. Okay. So this is when UV is an edge. But if there is an edge in the opposite direction, if VU is an edge, then we give the flow assignment to VU as the residual capacity of UV. Okay. So this is the kind of counterintuitive part. Okay. Going back to this example here. Okay. So SB is an edge, right? Now I'll be assigning BS a residual capacity of the flow assignment, which happens to be 0 here. Okay. So similarly, so AB is an edge. Now I'll also be having edge BA with capacity 10, which is a flow assignment. Okay. Now that is something really, really counterintuitive. Okay. So why should we do that? So the idea is, if I was talking about rerouting, right? So the residual network is basically to talk about rerouting the flow. Okay. So the idea is, I mean, at least the intuitive idea is what we want is a network where there should be an indication. So if the flow is not optimal, there should be a possibility of rerouting. And this rerouting happens to be a path. Okay. So eventually it happens to be a path. Okay. So what we do is, so we create a new network where if there was a flow assignment, in this case 10 from A to B, so we'll add an edge B to A with the capacity as 10, just to indicate that if needed, you can take this flow of 10 in the backward direction, because you had already assigned the 10 in the forward direction. In the rerouting process, you can take some amount back. Okay, so that is a kind of intuitive idea. And if UV or VU, neither of them is an edge, both of them have capacity 0, then we just set the residual capacity as 0. Okay. So now, yeah, so we just denote residual capacity. So remember that residual capacity is defined for V cross V, not just the edge, because even if there is an edge in the reverse direction, right, the residual capacity is defined. Okay. Now the residual graph is basically graph with the same set of vertices, but the edges are defined according to the residual capacity. Okay. So EF is set of all pairs UV where the residual capacity is non-zero. Okay, it can never be 0 because it's a feasible flow. This will be greater than or equal to 0. Since it's a flow assignment, this will be greater than or equal to 0. Okay, if it is 0, we just don't consider those pairs at all. So now I'll demonstrate with an example. This example is the same old example. It's from Erickson's book. Okay, so suppose this is our flow assignment: 10 for this edge, 0 for this edge, 5 for this edge, and the other side of forward slash is the capacity. Okay, so 20 was the capacity here, 10 was the capacity, 10 is the capacity, and so on. Okay, now the residual graph is following. Okay, so here this edge, okay, so the residual capacity of this edge in this direction, S2 whatever. Okay, so I think we labeled it as A, B, C, D. So S to A would be 10, which is capacity minus the flow assignment. But there is also an edge in the other direction here. That is because, so when you see AS, SA is an edge, okay, it has some flow. So by this definition, so SA is an edge, then AS will get the flow assignment of SA as a capacity. Okay, so this is a flow assignment. Equal to F of SA, flow assigned to. Okay. Yeah, so I can see and verify the other edges too. So here the flow assignment was 0, so only forward edge is present. The flow assignment was full 10, so there is only reverse edge here. And here for flow assignment is 0, that's only forward edge. Flow assignment was 0, there is only forward edge. Flow assignment was to the capacity, so hence there is only reverse edge. So here flow assigned is 5 and capacity is 10, so there are two edges. So 5 representing what more can be assigned, and 5 is what can be taken back. Okay, so similarly 5 representing what can be taken back because 5 was already assigned here. 15 is the residual capacity. Okay, so that is it. Is the definition of residual network clear?
Sir, can you explain the intuition of residual graph again? I'm not understanding the intuition behind it.
See, the intuition is, like I said, right? We want a network which helps us allow rerouting the flow. Okay. So the idea is, I mean, the thinking is very, very algorithmic in nature. Okay. So I mean, see, when you see the proof, I mean, it looks like very magical, but at least the thought process behind this, having this back edge is like, see, what do you mean by reassigning a flow? Okay. So when we reassign flow, the intuition is, so you are only manipulating this flow, okay? You're only manipulating this flow such a way that you have another feasible flow, probably with a larger flow value. So when you manipulate, maybe you might add this, okay? Or in some cases, this, so assigning 10 to this was a mistake. You should not send so much on that route. You want to send only 5. So then how will you do that? How will you formulate that? That will be indicated as, okay, I'll take this 10, I am allowed to take this 10 back if I need. Okay. So when I say rerouting is with respect to a path. So if the path basically chooses this, let's say this is the path. Okay. So this basically says that, okay, I'm assigning 10 here. Okay. But I'm taking that 10 back here. That means I'm losing that 10 from here. Okay. And so hence this 10 has to be rerouted elsewhere. That's all I can see. I mean, that's all I understood. I mean, when I see it for the first time, like I said, it looks fairly magical. Okay, so in fact, at that time it was a groundbreaking result in that way. Okay, so that's
like,
all. Yeah.
What do you mean by rerouting here? I'm not able to appreciate. You are saying it's magical.
Yeah.
But...
So when you see the proof, you'll appreciate it.
Okay.
Yeah. So. Yeah, any other question here? Okay, so whenever I say GF, the residual graph, this is the graph I mean. So only one thing is, in GF, I'm not keeping the promise of not having bidirectional edges, okay, which is allowed in GF. So though in the original network I said, okay, I want to get rid of these edges, okay. So of course, do you see why did we require that in the definition, staring at this? So here, so that was required in defining this residual capacity, okay. If I had edges in both directions, then there is a problem, right? So both conditions are applicable. So then I cannot define the residual capacity in this way. So it's not well defined at all, okay. So for that reason, we'll assume that there is no bidirectional edges, but in the residual network, it will have. I hope it is not confusing. Yeah, so we should be differentiating between the original graph and the residual network. The residual network is allowed to have back and forth edges, whereas original flow network, we will not. And I mean, if the graph had it, we would modify it accordingly so that there is no back and forth edges between a pair of vertices. Okay. Yeah, so now it turns out that if you take any S2T path in this graph, the capacity, minimum of the capacities along this path is a value of flow, amount of flow, which is still left over. That means you can modify the flow such a way that you can increase the value of the flow. Okay, so that is essentially the idea of Ford and Fulkerson. So, I mean, not the shortest, any S2T path in this network means something about the flow. And if there is no S2T path, that means that the flow is optimal. If the graph is disconnected, that is, there is no S2T, there might be an edge behind, I mean, there could be a T to S path, we'll not really worry about it. If there is no directed S2T path in this network, that means that the flow is optimal. These are the two primary observations, okay? So the first one, the moment you have a path, you can actually reassign the flow. It's basically like rerouting, okay? So reassign the flow such a way that the resulting flow is feasible but has value larger than the original flow. So now if you keep on finding a S2T path in the residual network and keep on updating the flow, at some point the graph will become disconnected, right? There may not be an S2T path because there are only finite number of S2T paths. Every time you are plucking out one S2T path, and or in other words, you can also imagine the flow can not exceed whatever the min cut value. So if the flow is keeping on increasing, this process can only continue finite number of times. Then we'll argue that the moment you don't have an S2T path, the flow has to be optimal. Okay, so these are the two things that we are going to do now. So I'll just formally define the path. Okay, nothing much there. So let GF be the residual network of a flow network G. Any S2T path in GF is called an augmenting path. Okay. So the term that I use, right, flow rerouting, is in fact called flow augmentation. Okay, so you're augmenting the flow. This path allows us to augment the flow. Yeah, so that is what we are going to see now. Okay, so let's take this old example from Erickson's book. Okay, so this red colored path is an S2T path in the residual network. Okay, so I'm using the same residual network as here. It's the same residual network. I'm taking this path. Okay. Oh no, this path. So in fact, the same thing can be done for any S2T path. Okay, so let's take this path. Now let's just try to understand. So, okay, so this path, if you look at travel along path, this path, what is the minimum capacity here? Minimum edge capacity? So 10, 10, 5, 5, 15. So minimum edge capacity is 5, right? Right. Yeah, good. So now I claim that I can modify this flow such that the new flow will have a value of 5. Okay. So how am I going to modify the flow? So I look at this path. So the minimum capacity is 5. Okay. So what I do is I add a flow of 5 along this path for every edge. What do I mean by that? So let's go back to the original. So here this was 0. Now I'm adding 5. That is, this edge gets a flow assignment of 5. But there was no edge this direction, right? So this path has edge in this direction, but I'm assigning 5. What do I mean? I'm taking away, so the flow was 10 assigned initially, but I'm taking away 5. That is, I'm rerouting that, whatever that it could be a traffic or transportation or whatever. Okay, so this 5 is taken out from here. See, 10 was arriving here, 10 was available. So earlier 10 was routed through this edge. Now I'm taking away that 5 and I'm assigning it to this. Okay, so along this path I'm assigning a flow of 5 for every edge. If it already had a value, we'll increase it by 5. Okay, so now when I say I assign 5 to this, I basically mean is I take away the 10 out of the 10 assigned here, I take away 5. Okay, so this is how the new flow will look like. So along this path I'm adding 5. So here for this edge, adding 5 means taking away 5. Okay, so that the flow conservation property is preserved. Okay, so now if you see, value of the flow is 10 plus 5. So I've added 5 along all. Okay, so the original, so again Hello? Here, yeah.
Sir, yeah. Sorry to interrupt, but when you are adding 5, aren't you crossing the capacity from this vertical edge, which is going from bottom to top, the red vertical edge?
Yeah, the red vertical edge was not there in the original graph, right?
Yeah, but like I'm not able to understand.
Yeah, so when I say in the opposite direction, if I'm adding, that means I'm taking away 5. That's all. See, earlier the graph, the edge in the original flow, this edge had a flow value of 10, right? Now
Yes.
I'm assigning 5 in the opposite direction. That means I'm reducing this value to 5. I'm basically taking out that flow amount of 5 and rerouting it to some other edge. We are sending it to some other edge.
Okay.
Okay, so that's exactly it. So yeah, so this is the resulting flow. Okay, so yeah, maybe I'll just zoom in, zoom out a bit. Is it visible or is it too difficult to see? Yeah, I don't know if I can have both the graphs together. Okay, see, the original flow was this. Now what I did is I updated it to 5. But then, so 10 was incoming here, right? So that 5 should go, but that is directed by this path. So this path will ensure that 5 is assigned here. So this was 0 initially, but 5 was assigned here. Okay. So the updated flow here is what we did is the only change is reflected along this path. So this path, so there was a flow of incoming flow of 5, but then there was an opposite direction edge in the residual network, and that was in the path, okay, with the edge value 5. So we are assigning 5 means we are taking away 5 here. So we are rerouting. So this new flow assignment will make it as 0 here. So it was 5 earlier, made it as 0. 10 here, made it as 5. It was 0 here, made it as 5 here. What else did it change? So it was 10 here initially, made it as 5. Sorry, 5 here initially, made it as 10. So this became 15. Sorry. So we need to define this formally, of course. Okay, but is the idea clear? So in this path, there are 2 reverse direction edges compared to the original network. The original network is here. Yeah. So direction was A to B and C to D. Now this is B to A and D to C, or the other way around. Okay. So yeah. So now when we have a path which takes edges in the opposite direction, what we do is we reduce the flow assignment for those edges. And if you are taking, if this path agrees with the original graph, it's in the same direction, the edge direction is the same as in the original graph, that means we are increasing the flow. So we are increasing the flow here. Okay. So now I'm going to define it formally. Okay, maybe I'll go through this another example and then define it. Maybe or I'll define it first. Okay. So P be any augmenting path. Okay. So augmenting S to T path. So remember that an augmenting path is S to T path, but in the residual network. Okay. So F be the minimum capacity of edges along this path. Okay, you run through the path and look at the minimum capacity, but the residual capacity, not the capacity in the original graph. Now we update the flow as follows. So the new flow we call it as F prime. F prime of UV is if the edge in the path is the original edge in the graph. Okay, yeah. So take any UV edge in the graph. So if it is in the path as well, then you update the flow. That is F of UV plus F. Now, if the opposite edge was in the path, okay, so UV was edge in the graph, G, but whereas GF had VU, and VU was taken in the path, that's exactly what is here, okay. So this is the edge, but in the graph, the edge was in the opposite direction here, okay. So now what you do is, this value of F, you take it away. That is, the new flow is F of UV minus F. Those edges they don't lie in the path, we don't do anything. We just keep their flows as it is. That's exactly what we did here. Okay. So you look at this path, go along the path. Okay, look at this edge. This edge was present. So along this path, what is a capital F? Capital F is phi. Okay, minimum capacity. When I say capacity, capacity in the residual network. That is minimum value of CF, not C. Okay. Now you take that value. Now we are going to update the flow accordingly. Okay. So this edge is also edge in the graph. It's in the forward direction. So I'll add the flow. Okay. So add phi. That's what it is. This edge, this is in the opposite direction. This is reverse edge compared to the original graph. I'll take away phi. Okay. So the flow is reduced to phi. Now this edge is in the forward direction. Now I will add phi. This edge is in the opposite direction. So I take away phi. So this was phi. I'll reduce it by phi. So this becomes 0. And what else is there? Yeah, this edge. Yeah. So this edge 15. So what was the original flow assignment? It was phi, but I'll add phi here. It becomes 10. Now if I look at this is a feasible flow, right? So is there any vertex which violates conservation or beyond capacity at any edge? Is the definition that we gave and demonstration in this example clear? So all we do is consider an S2T path. Now it's about the orientation of the edge in this path, that is path in the residual network and in the original graph. If the orientation match, then you add the value F. Capital F is basically the minimum capacity along this path. You add that F. If the orientation is in the opposite direction, you subtract that F. That's all we did here. And those that don't have anything to do with this path, those edges that don't that are not contained in this path, you keep it untouched. Nothing changes. So I'll just demonstrated one more example. This is taken from CLRS book. Okay, so this is S and T. These are P1, P2, P3, P4. Okay, or F1. I don't know. Okay, P or V. Okay, sorry, my view is very bad. Okay, so these are the assignments. Okay, so 16 is the capacity, but 11 is the flow assignment. 13 is the capacity, 8 is the assignment, and so on. So you can verify feasibility condition here. Now this is the residual network here. So 5 is left over. So 5 and 11 was the flow assignment. So you keep it as a backward edge and so on. Okay. Now this is an S2T path in the residual network. Okay. So 5, which is in concurrence with the original graph. 4, that is opposite direction to the original graph. And then 5 again. Okay. Now what is the updated flow? So here is updated flow. Okay. So how did we update? We added. Yeah. So look at this graph, this path. Okay. So what is the minimum capacity here? Capital F. So 5, 4, 5, 4. Right. So 4 is my capital F. Let me just write it here somewhere. Capital F is 4. Okay. So now you add 4 along the path. So you take this edge. The original assignment was 8. 8 plus 4, 12. Now this V2 to V3. Okay. Okay. Yeah, I'm very sorry. Okay, so I'm reading this VSP for some reason. This is V, right? This is so much of glare on my screen that I can't really. Okay. Okay, so V2 to V3 is an edge in this path, but in the original graph it is V3 to V2. Okay, so we'll take away, so 4 was the assigned value, we will take away 4. Okay, so now there is no assignment, flow assignment to this. Okay, now V3 to T, the edge is in the forward direction, so we need to add 4. 4 was the minimum capacity along this path. Okay, so I added 4, so this became 19. This is a corresponding residual network. Okay, yeah, is it clear? It's fairly mechanical process. Okay, you go along the path, you look at the orientation of the edge. If it matches, update, add the flow value by this value, capital F. If it is in the opposite direction, you subtract the flow value. It's basically pulling away the flow or rerouting the flow elsewhere. Okay, so yeah, so now let's see what is it we want to verify. So what we did we started with the flow. Okay, and we constructed this residual network GF. Okay, with the residual capacities, we took an augmenting path. If at all there is one. If it is not, if it is not there, then we'll see what to do. And we updated the flow, so we got a new flow. Now the first thing is it feasible? Well, these two examples in the picture, they are feasible. You can verify that they are feasible. Okay, I haven't verified one by one now. I leave it to you to verify. Okay, you can verify that these are feasible flows. So in fact, for an arbitrary graph G or arbitrary flow network G, we can in fact verify that F prime is indeed a feasible flow. Okay. So first thing is F prime is a feasible flow. The second thing is, so given that F prime is a feasible flow, what is its value? Now value of the flow, so remember that we are taking an S to T path. An augmenting path is from S to T. So the first edge in the path is always outgoing, right? So the value of the flow, so what is the value of F prime? Can somebody tell? So orientation of the first edge, S to something, is always along with the orientation in the graph, right? Consistent with the orientation in the graph. Yeah. Hello.
F prime is 23.
Yeah, that is in this example, but in general, what is it?
So
With this definition,
old F plus the minimum that we found in our augmenting path.
that is capital F, right?
Yeah.
Yeah, very good. So that is all. Okay. So once the moment we prove that it is feasible, the value of F prime is going to be value of F plus, it's not just greater or equal to, in fact it is greater than value of F plus capital F. Capital F is some non-zero value, right? The way we have defined, if there is an augmenting path, the minimum capacity will be a non-zero value, because if it is 0, then we are not even considering that edge at all. Okay, so yeah, so all it remains is to show that F prime is feasible. Okay. Okay. So can okay, I'll take 5 minutes. Okay, I'll just complete the feasibility condition. First, to show that F prime is feasible. Okay. So consider any edge. E. Okay. Now there are 3 possibilities. So case 1, UV is in P. Case 2, VU is in P. Case 3 is neither of the two. Okay. The remaining condition, neither in P nor VU in P. Okay. Now, if UV is in P, what is the value of F prime? Let's go back to the definition. It's FUV plus capital F. Right? Now, what is capital F? Is the minimum residual capacity along the path, right? That means this is less than or equal to CFUV right? It cannot be more than the residual capacity of the edge. Now, what is the residual capacity of the edge? If the orientation is according to the original graph, the residual capacity is how much? Where is it? Let's go back. It's far off. It is CUV minus FUV, right? So this is, let's just write down again. This is less than or equal to F, I'm very sorry, FUV plus CUV minus FUV, which is equal to CUV. So, or in other words, F prime UV is less than or equal to the capacity. There is a less than or equal to here. It might be strict, in fact, because CF UV may not match with capital F. Capital F could be significantly smaller. Okay. So, if UV is in path and its orientation is as per the original graph, then we know that the capacity bound satisfied. Okay. Now, if VU is in P, is it satisfied? What is F prime UV? F UV minus F, right? This is of course less than FUV, less than or equal to CUV. So those in the opposite direction, we are reducing the flow. So of course, feasibility condition will satisfy, right? And in this case, F prime UV is equal to FUV. So we started with the feasible flow and we didn't change the flow value. So in all three cases, so the first case, UV was in the path and orientation is according to the original graph, and the corresponding flow assignment is within the capacity. If it was in the opposite direction, of course, we are only reducing the flow value, so it will be within the capacity. In other cases, there is no change in flow value. Or in other words, F prime is indeed a feasible flow. So therefore,
Sir, in case 2, shouldn't we also prove that F prime is positive, like it's not negative?
yeah, that's a very good question. Yes, you're right. That's a very good point I missed. Yeah. So yeah, we should also see that this is positive. Okay. So now, yeah, since F is less than or equal to CF UV, which is equal to FUV, F prime UV is equal to is greater than or equal to FUV minus FUV, which is 0. Yeah. So very good point that you have pointed out. Okay. Yeah. So when you say feasibility, I mean, see, since we are reducing the value, we should ensure that it is not negative. Okay. But that is pretty much there from the definition. So remember that the value of F is at most the capacity of this edge, right? Yeah, which is CFUV. But how did we define CFUV for a reverse direction edge? As the flow assignment, F of UV. Okay. So hence F prime UV is at least, so F is at most FUV. So this is at least FUV minus FUV, that is 0. So it is non-negative. So the value that you have reduced will not be more than the flow assigned value, because capital F is at most f of uv, which is the capacity of the residual capacity of uv. Yeah, good. Yeah. So what we have concluded is f prime is a feasible flow. Now, just as I had discussed, capacity of or value of f prime is value of f plus f. Prove this. Okay. So I'm leaving the proof to you. I mean, it's not much there to prove, but anyway. So let's just take stock of what we did so far. So what we said is, if there is an S2T path, that is an augmenting path in the residual network, we can always obtain a flow whose value is larger than the existing flow. Now, only thing that we need to argue about is, what if there is no augmenting path? So next lecture, what if there is no augmenting path? So indeed, if there is no augmenting path, we can see that S and T are separated. There is no, so in fact, there will be an S to T cut, and then we'll see that the flow should match the capacity of that cut. Okay, so I'll do it in the next lecture. Srinivasa, can you stop the recording?